Okay, so we will just continue from here. Let Now let us see a question. Let A be the set of all triangles in a plane, and R be a relation in A defined by R, such that triangle 1, comma triangle 2, such that triangle 1 is congruent to triangle 2. Show that R is an equivalence relation in A. So for equivalence relation, as we have seen, we need to go for all the you can say types of relations, that is reflexive, symmetric, and transitive. The given relation satisfies the following properties. Reflexivity, let A be a arbitrary triangle in A, then triangle uh, is congruent to triangle, implies that triangle comma triangle belongs to R for all values of triangle in A. That is, therefore R is reflexive in nature. Symmetry, let triangle 1, triangle 2 belongs to A, such that triangle 1 comma triangle 2 belongs to R, then triangle 1 comma 2 belongs to R, implies that triangle 1 is congruent to triangle 2, or triangle 2 is congruent to triangle 1, or triangle 2 comma triangle 1 belongs to R. R is symmetric in this case also. So transitivity, let us say there are three triangles. Triangle 1, triangle 2, and triangle 3 belongs to A, so that triangle 1 comma triangle 2 belongs to R, and triangle 2 comma triangle 3 belongs to R, then triangle 1 comma triangle 2 belongs to R, and triangle 2 comma triangle 3 belongs to R. Triangle 1 is congruent to triangle 2, and triangle 2 is congruent to triangle 3. So triangle 1 is congruent to triangle 2. Triangle 1 comma triangle 3 belongs to R. R is transitive. Thus R is transitive, reflexive, symmetric, and transitive in nature. That's why it is an equivalence relation. Because it was congruent, so it was not very difficult here to uh, prove. Okay, because both the triangles, besides that, both are congruent in nature. That's why it is very simple to go for reflexivity, symmetric, and transitivity here. Let us go for one more question, the same background. Let A be the set of all lines in XY plane, and let R be a relation in A defined by R, uh, L1 comma L2, such that L1 is parallel to L2. So that R is an equivalence relation in A. Find the set of all lines related to the line y is equal to 3x plus 5. So again, for equivalence, we have to go for reflexive, symmetric, and transitive. So reflexivity, L is parallel to L. L comma L belongs to R for all L belongs to A. Thus R is reflexive, symmetric. L comma L, L1 comma L2 belongs to R, implies that L1 is parallel to L2 and L2 is parallel to L1, obviously. So L1, L2 comma L1 belongs to R. Therefore R is symmetric in nature. Transitivity, for that you can understand like let the L1, L2, L3 belongs to A, such that L1, L2 belongs to R and L2, L3 belongs to R, and L1, comma. So L1 is parallel to L2 and L2 is parallel to L3. It's obvious that L1 is parallel to L3. That's why L1, L3 belongs to R, and R1 is transitive in nature. The family of lines parallel to the line is given by y is equal to 3x plus k, because it's a constant. A constant can be any case, any real number, so we can have any type of value there in this case. So by this method, we can say these two examples we have seen. The first one, the second one. Both examples I think is clear to students who are able to see this. I'm just going ahead with one more different example I'll take. Yeah. So we can also go forward. It will come back after some with the type of revision we can do. Yeah. So let me see if any other part we can take for discussion. And then obviously we will go forward to, okay, we can take this question as a reference, the 15th one. Give an example to show that the union of two equivalence relations on a set A need not to be an equivalence relation on A. Means they require union of two equivalence relations on a set A. Need not to be an equivalence relation on A. So let R1, R2 be the relations on a set A. 1, 2, 3 given by R1. What is R1 here? 1, 1, 2, 2, 3, 3, 1, 2, and 2, 1. R2 is the same and 1, 3, and 3, 1. Then it is easy to verify that each one of the R1, R2 is an equivalence relation. R1 union R2 is not transitive as 3, 1 belongs to R1 union R2, and so it's not. So hence we can say with the help of this R1 union R2 is not an equivalence relation. Okay. So what actually is being detailed here is actually we need an example to show the union of two equivalence relations on a set A need not be an equivalence relation on A. So that is the question. So we have taken one set A of elements 1, 2, 3, and R1, R2 we have defined as the relation. We have taken a condition of 1, 2, 2, 1 there and 1, 3, 3, 1 here. So here we can say that R1, R2 is an equivalence relation. So obviously it will follow all of the conditions of uh, the conditions that is transitive, symmetric, and reflexive here. But union of both will lead to have everything. It is not transitive as 3, 1 belongs to union and 1, belongs to the union of this, but 3, 2 does not belong to the union. Hence, it is not an equivalence relation. Okay. This we can have a review again if required. We'll come back to the review again if required. So what is equivalence classes? Let R be an equivalence relation in a set A and let small a belongs to A, then the set of all those elements of A which are related to A is called the equivalence class determined by an A and is denoted by bracket A. So this bracket A is equal to B belongs to A such that A comma B belongs to R. Two equivalence classes are either disjoint or identical. The two equivalence classes are either disjoint or identical in nature. So So in this case, what we can say that equivalence relations or equivalence classes, let R be an equivalence relation in set A, and let A belongs to the question is classes we will have to see. Let R be an equivalence relation in set A, and A belongs to set of all those elements of A which are related to A. It's called equivalence class determined by A and is noted by this. So two equivalence related classes are either disjoint or identical. And important reason is an equivalence relation R on a set A partitions the set into mutually disjoint equivalent classes. We'll just have a review of the one example we'll see. On the set Z of all integers, consider the relation R is such that A comma B such that A minus B is divisible by 3. We have to show here R is an equivalence relation on Z. Find the partitioning of Z into mutually disjoint equivalence classes. The relation R on Z satisfies the following properties. Reflexivity, let A belongs to Z, and A minus A is 0, which is divisible by 3. Okay, divisible by 3. Therefore, A is related to A for all A belongs to Z. A is reflexive in nature. Symmetry, let us see. So A comma B belongs to Z, so that A is related to B, then the E minus B divisible by 3. Minus of this is divisible by 3, B minus A divisible by 3, and B is related to A. So here also we can say it is symmetric in nature. Transitivity, let us see. Let us say ABC belongs to Z, and then A is related to B and B is related to C. Then the A minus B is divisible by 3, and B minus C is divisible by 3. A minus B plus B minus C is divisible by 3, and A minus C by 3, and then we can say that thus A is related to B is related to C, is implies that A is related to C for all ABC belongs to Z. So therefore R is an equivalence relation on Z. Now let us consider 0, 1, 2. For 0, let us consider few cases of 0, 1, 2 as mentioned. X belongs to Z, so that X is related to 0. X minus 0 is divided by 3. So minus 6 minus 3 is 0, 3, 6, 9. We can say 0, bracket 0 is similarly for bracket 1. We have minus 5, minus 2, 1, 4, 7. And similarly, we have the other cases. So clearly, these are the mutually disjoint, and Z is equal to bracket O union bracket 1 bracket 2. So looks like we have to revisit here whenever we require. Okay. So so we're done with the relations, looks like. So that's why what I will do, I will just go with few other questions because relations, I think, more need to be revisited properly. We will have to revisit the cases here. Yeah, one more question, I'll just go here. That A is equal to X belongs to Z. x is greater than equal to 0 and less than equal to 12. So r is equal to a comma b such that a minus b modulus is a multiple of 4 is a reflexive, symmetric, and transitive. Show, find a set of elements related to 1. Now we have here A as from 0 to starting and 12 is ending. Obviously, if there is a set and R satisfies the following properties, reflexivity, let us check, let A be a arbitrary element of A, then A minus A is 0, which is a multiple of 4. A is related to A for all A belongs to A. So R is reflexive in nature. And again, we go for the symmetry part. A minus B is a multiple of 4. Here we modulus is multiple of 4. Negative of that is multiple of 4, or we can say it's symmetric in nature. So transitive, you see, uh, A is related to B and B is related to C, then A is related to B. So A minus B modulus is multiple of 4. B minus C modulus is multiple of 4. A minus B modulus is 4K1. 4K2 is for PC1. B minus C modulus. A minus C modulus is modulus of A minus B minus C, 4K1 minus 4K2, and 4 in bracket K1 minus K2, where 4 outside and K1 minus K2, which is a multiple of 4. A is related to B is related to C, and A is related to C. So this is R is transitive in nature, thus R is following up. So R is a equivalence relation. One bracket will be X belongs to A, X related to 1, X belongs to A. Modulus of x minus a is a multiple of 4, 159. The required set is 159. The multiple of 159 is the set here. The required set is 159. Okay. So we have covered this particular chapter of relations very short. We'll come back here if required with few other questions to practice. I'll just mark this particular question also as you can say a review question. Okay. So we'll come back to this particular part again just to work on the questions.